Alrighty, hello friends, it's Miss Summers. Hope you're doing well. Got your notes today. Alright, for the rest of this week, this unit, we are going to be talking about oceans. Alright, so we spent most of this hydrosphere talking about freshwater. We talked a little bit about the water cycle and groundwater, aquifers, rivers, wetlands. Alright, how people are messing it up. Alright, and that's important. We should care about that because we remember freshwater is an important for human survival. It's important for food production, agriculture, energy production. Alright, so that's why we've been focusing on that. Alright, but today we're going to switch gears. We're going to talk about the ocean because the ocean, even though we can't use the ocean for things like agriculture, we can't use the ocean for things like obviously like we can't use it to grow food or to drink or whatever. It's still kind of a big deal because the majority of our planet is indeed covered in oceans. So we're going to look at what is under the ocean, the features. We're going to look at a little bit about properties of ocean water, okay, what makes it different, and a little bit about waves. All right, so let's start with this question. What does the bottom of the ocean look like? You don't need to write anything down here. Is it covered in sand or silt or clay or plants or mountains or valleys or anything? All right. This is a question that has long plagued humanity. All right, for a long time, obviously, people used oceans to travel, but you couldn't see what was at the bottom. So people really didn't have any idea what was there. So there's kind of been this notion that the ocean was notion of the ocean. That rhymes. Haha. All right, there's been this idea that at the bottom of the ocean it was completely flat and barren and featureless and there couldn't possibly be any living things down there, right? Because there's no sunlight, so there can't possibly be a food chain. All right. And it wasn't until very recently in human history, about 70-ish years ago, all right, right around the end of the 40s, 50s, that humans started to develop the technology that was needed in order to look at the ocean floor. All right, so we're going to take a very quick little look around the ocean floor. I got this little video here. All right, and we're going to look at what would it look like if we drained all the water away? What would the bottom look like? Okay. So we have it here. All right, we're pulling all this water away. These darker grays are areas where it's deeper. These lighter grays are where it's more shallow. All right, so you can see like off the coast of Florida, it's pretty shallow, and then it drops off in the Gulf. All right, here's your continental shelf, the edges of your continental crust. And here at the bottom of the ocean, it's not actually flat at all. There's bunches of little stuffer stuffs. Here's our mid-Atlantic ridge. I know you cannot see that. It's super fuzzy. All right, we talked about this mid-Atlantic ridge, the mid-ocean ridge, when we talked about big geosphere, how this happens where you have divergent boundaries. All right, now the neat thing about this ridge is it doesn't just go between, America, the Americas and Europe, or South America and Africa. It goes around the entire world, about 80,000 kilometers, all right? We also found these little narrow trenches that go really, really super deep, all right? With technology, we can see how the seafloor is moving, all right? The East Pacific Rise is the fastest spreading crust. That's where the plates are moving apart the fastest. Little historical note here. We have the final resting place of the Titanic, about 4 kilometers below the surface. All right. And if we keep moving north, we can see our mid-Atlantic ridge here. All right. Cuts right across where Iceland is. All right. So stuff is happening at the bottom of the ocean. Stuff is being made. That's what we want to know about. All right. So I'm going to jump back. Here, present, fantastic. All right, this is where you need to write stuff. So, the landscapes found deep beneath the oceans are just as dramatic as you would find on shore. There are mountains, there are peaks, there are valleys, there are plains, there are trenches. There's all sorts of shenanigans going on. We're going to look at it, how it gets there, how it's made, why we care. Okay. So our first feature that we're going to visit, is the good old mid-ocean ridge, because we've already talked about that. We've already talked about these good old mid-ocean ridges. We remember that a ridge is a mountain range, okay? A ridge is a high place. All right, it's an underwater mountain range that forms that divergent boundary as a result of magma coming up to the surface. So here, new crust is made, which we talked about that in Unit 3. This is not new. All right, we remember convection currents is what's causing these plates to move apart, and that's why these plates are moving away, and that's allowing this new crust to form here as magma pops up. All right, you can see the young crust here in red. So we have a nice view of that mid-Atlantic ridge right here. We have that nice view of the East Pacific Rise. Remember, this is spreading faster. That's why this band of new crust is wider than this band. This one is taking its sweet old time. This one's going a lot faster. All right, so we already talked about that. But what happens if I go away from the ridge? Okay, let's say I'm here at the ridge and I start making my way towards North America. Okay, what am I going to see? I'm going to see the Abyssal Plain, or the basin. All right, this is kind of what it sounds like. So when you hear somebody say like the abyss, okay, that's where it's really dark and there's nothing there. All right, here we have a plain. So here, this is relatively flat. All right, it's usually between 3,000 and 6,000 meters. I don't need you to memorize these numbers. All right, but I want you to know that it's between the rise and the ridge. Now we're going to talk about what a rise is next slide, so don't worry about that. Okay, now the reason these abyssal plains are of interest is because they take up, okay, if we were to drain the water away and just look at Earth as a whole sphere, abyssal plains would be the majority of it. They cover over 50% of the surface. They are pretty flat, pretty smooth, and not gonna lie, we don't really look at them that much. All right, so right here, these the abyssal plain. Now, we said the abyssal plain goes from the ridge to the rise. Let's look at what the rise is. The Continental Rise, all right? So picture it. I'm at the ridge. I start walking towards North America. I'm going across the abyssal plain. It's flat. There ain't a whole lot to look at. It's kind of boring, not gonna lie. Now, I make my way towards the continental crust. Remember, continental crust is thicker than oceanic crust. So here, the rise is the bottom of this slope, all right, where the oceanic crust meets the continental crust. Now, what's interesting about the rise is because it's at the bottom of this slope, any sediments that kind of fall down because of gravity kind of get stirred up here, so you have a very murky area, a very high turbidity. Remember, we talked about turbidity on Friday. I think it was Friday. Yeah, it was Friday. All right. Turbidity is how cloudy the water looks. All right. So here we don't have a ton going on, but we do have that change in water quality. All right. Now, I've crossed the abyssal plain. I've gone through this murky water of the rise. Now I gotta go up the slope. The slope, not gonna lie, not a lot to look at here, is very steep. All right, it is just kind of straight up this drop off. All right, where you go from relatively shallow water to super deep water. All right, because it's so steep, there's not a ton of resources here, so you're gonna have minimal living things kind of hanging out here around the slope. Way less things than on the shelf. All right, the shelf is what we're familiar with. We know the shelf. We're familiar with the shelf. All right, the shelf is the shallowest part of the ocean. All right, when you go to the beach, okay, and you go out and you charter like a deep sea fishing vessel or whatever, you are still probably on the continental shelf, all right? Because it's so shallow, you have very warm water that is being heated by the sun. Because you have sunlight, that is a resource that living things use, mainly producers use, to make food. So you have lots of biodiversity here. You have lots of critters running around, all right? So it is just what it sounds like. It is a shelf. It is a shelf, okay? So here we are frolicking at the beach, all right? The width of the continental shelf depends on which continent you're talking about. So like you looked at like where Florida was in that video, there, especially on the Gulf side, that continental shelf is pretty wide. But in other areas, it's a lot slimmer. Just kind of depends. All right. Snazzy, snazzy, snazzy. So that was our little journey from the ridge, the mountain, across the Abyssal Plain, the flat part, up the rise, all right, where the water is all murky, up that steep slope, onto the continental shelf. All right, but we're not done. There's still some other shenanigans to look at. Trenches, my favorite part of the ocean. Are trenches my favorite part of the ocean? I don't know. They're pretty cool though. All right, a trench, we remember, is this underwater canyon. It's very narrow, formed at convergent boundaries, not divergent, convergent. Trenches are formed at convergent boundaries. They are the deepest and coldest places in the ocean. All right, so the depth of these trenches is going to depend on how deep your subduction zone is, how much it's pulling that plate under. All right, you can see trenches from satellite views. All right, so we have one here, right around the coast of Greece and the island of Crete and Turkey. This is called the Hellenic Trench. Hellenic is in reference to a historical period in ancient Greece. All right, but you can see it's a little bit darker. It's a little bit darker than the other ones. All right, now, what's really snazzy about trenches? At trenches, even at the Abyssal Plain, let alone trenches, sunlight cannot get to the bottom of these trenches. It just cannot. The light gets scattered and it is completely dark. Zero light. Like none. Right? But what's amazing is that at these depths, you still have these super fun little critters running around. Alright? So these are pictures of some of the fish life that you can find at the depths. All of these two pictures were taken in Challenger Deep, which is the deepest part of the Marianas Trench. So the deepest part of the deepest trench, it's about 11 kilometers down, which is a little over 7 miles. All right, this is called a grenadier fish. I think it's really pretty. I forgot what these little guys are called, but there's lots of them. They're feeding on like a little like bait fish. They have like some little like chummy chums. All right, and then of course we are all probably familiar with what this gal is. It is your classic angler fish. All right. A lot of these organisms have really snazzy adaptations to living in complete darkness. Let's take a look at this anglerfish just for funsies. So obviously this is a predatory fish. It eats other stuff. It eats other fishies, and it gets its name because it uses this little like light that's coming out of its head, and it is able to create its own light source. All right, that light source attracts in smaller fishies like these guys here, and then that anglerfish is able to snatch it up with this protruding lower jaw. All right, these animals, if you were to bring them to the surface, all right, would not survive. All right, because they are used to living 7 miles below the surface of the ocean. All right, they are used to literally thousands of pounds of pressure pressing on any square inch of them at one time. All right, so if you were to pull them up towards the surface, okay, if you've ever been scuba diving, you might know what this is. When you scuba dive, you have to come up slowly so that you don't get these like big air bubbles forming in your bloodstream. It's called the bends. It's not fun. All right. These organisms, if you brought them up to the surface where the pressure is a lot lower, their little air pockets inside their bodies would expand so quickly it would kill them. All right, so it's very hard to study these organisms in their natural environment because A, it's really hard to get to, and we can't bring them to us. So pretty snazzy. Now you might be saying, Miss Summers, how are they eating down here? They ain't got no sunlight. Where are your producers at? What are they eating? All right, there's a couple of things that they're doing. One, depending on where you're at, there are little bacteria that instead of using light to make food, they use chemicals in a process called chemosynthesis. It's kind of like photosynthesis, but not. And two, a lot of these guys are scavengers. They eat what's called marine snow, which is like this debris, like the decayed remains of like other stufferkins, that just kind of floats down, and they just are happy to pick that off. It's pretty cool. All right, moving on. So let's come out of the trenches for a minute. Let's come out of the trench, and we look around, and we see a seamount. What is a seamount? It is an underwater mountain. Now you might be saying, Miss Summers, is that like a mid-ocean ridge? Kind of. A seamount is an individual mountain / volcano / whatever. A ridge is a whole system of them. That's what's different. All right. Once these get tall enough, okay, if you're a seamount that is a volcano and it's continually producing lava and it's building up on itself, once it breaks the surface, it is now an island. It is no longer a seamount. All right, like good old Hawaii. Good old Hawaii. All right, all of these started as underwater volcanoes. Remember, Hawaii is formed on a hot spot, not on a plate boundary. All right, so all of these formed underwater until they built up enough to reach the surface. Cool. All right, so you can find a bunch of really snazzy stufferkins below the surface of the ocean, but the ocean is also in part responsible for a lot of snazzy features on land as well. And again, we've talked about some of these. We talked a little bit about barrier islands when we talked about erosion. Remember, barrier islands are these very narrow islands that are off the coast of mainlands or larger pieces of land, like this one here. This is good old Long Island, the island. If you were from New York, it's the island. The island. All right. Barrier islands are constantly moving because of ocean dynamics. We talked about that. When we talked about erosion, we saw that one video with the one guy, and he was talking about like the wave energy, how in the wintertime the wave energy is higher, so sand gets taken away from the beach. It's eroded. But in the summer, the wave energy is lower, so the sand gets put back on the beach. The longshore currents, that's when the waves come in at a diagonal, and it pulls the sediment straight back. So these islands are zigzagging their way, either north or south or east or west or whatever. All right. So barrier islands, it's important to know like what's going on with barrier islands because people use them as a resource. People either live there or they use it for work, be it like a tourist industry or like a fishing industry or whatever skis. So you want to be aware of how that land is moving because we can't stop it from moving, so we need to be prepared for it. All right. The barrier islands of North Carolina include the world-famous Outer Banks that go all the way from the this northern part. Okay, this is up here is Corolla or Currituck. It's where the Red Lighthouse is. All right, all the way down Kitty Hawk. That's where the Wright brothers flew the first flight, heavier than air machine, on December 17th, 1903. Pretty fun. I've been there so many times. I know that day by heart. That's so fun. Yay. Down through the Capes, Cape Hatteras, Ocracoke Island, all that fun stuff. Okay? Cool. So, those are just some of the things that, some of the landforms that ocean dynamics form. So let's take a look at ocean water itself. We're going to look at something called currents tomorrow. So in order to understand currents, you kind of have to understand what waves are and also the difference between freshwater and ocean water. So what makes ocean water so darn special? You already know this. It's the salinity. Salinity, if you don't know what this word is, all right, but you know a little bit of Spanish, you'll recognize SAL, sal. Okay, if you were at the dinner table, okay, and somebody asked to pass the sal, that's the salt. That's the salt. It's the amount of dissolved particles. It's usually sodium chloride, which is what we use for table salt. And in ocean water, on average, it is 35 parts per thousand, which means if you took the water, divided it into 1,000 little pieces, 35 of them would be salt. And that's all that means. All right. Ocean water also has various temperatures, depending on what part of the ocean you're in. Okay, remember that continental shelf, where it's really shallow, is going to be a lot warmer because it's being heated up by the sun. Whereas the further down you go, the colder it gets, all right? So on the surface, all right, we have, this would be like in a very tropical region where the surface temperature is 22 degrees Celsius. Yeah, 22, Miss Summers, that's really cold. Celsius. All right, as I go down and I get less and less thermal energy from the sun, beep, it goes down to being closer to about 2 degrees Celsius, which is almost freezing. All right, that's going to be important when we talk about density currents tomorrow. Okay, some water is colder, some water is warmer. All right, so let's talk about waves. Let's talk about what waves are. Let's talk about what waves do. What are they? A wave is a rhythmic movement that's carrying energy. Okay, a wave is how energy moves. Like a light wave or a sound wave. All right, in the ocean, waves or energy is moving through the seawater. All right, so we're going to look at different parts of wave. This is kind of a little physics intro, a little physics lesson. Maybe if you've taken physical science, maybe this is a review. I don't know. If you take physics later, this will be stuff you already know. All right. A wave is made up of 3 parts, okay? We have a crest and a trough. So the crest is the highest point. The trough is the lowest. All right, so if you're sitting at the beach, all right, wherever that top is, where it starts to kind of fold over, or crest, that's why it's called that. There's that. The trough, you can think of like an animal trough where you would like put animal feed or water. That's at the bottom. All right. The wave height is important. The wave height, the distance between the crest and the trough vertically, so this way. So how far is it from the lowest point to the highest point? And then the wave length. The wave length is how far apart 2 waves are from either crest to crest or trough to trough. All right, so we have wavelength, wave height, our trough, and our crest. Now, how does this change wave height and wavelength? How does that change as you get closer to shore, further from shore, whatevskis? All right. So as the wave is passing through the ocean, all right, these water molecules are being disturbed up and down, so they're moving up and down, but they're not being pushed forward or backwards. So the water itself is not like moving closer to shore or farther away from shore, which then is kind of weird to think about because we see waves like coming towards us. That's the energy coming towards us, not the water from, 100 yards out or 200 yards out or whatever. All right, so you may have remembered this diagram from geohazards. We talked a little bit about tsunamis. All right, a tsunami is a ripple or a wave. Remember, earthquakes release energy. Waves are how energy moves. All right. We remember that tsunamis, when they're out in open water, when they're in very deep water like this, they move very quickly, but their wave height is very small. They're very, very, very short waves. There's not that much difference between the crest and the trough. But what happens once you get to the Continental Rise and the Continental Shelf, all right, the wave starts to slow down, all right, which means the wavelength decreases, all right, so the amount of space between this crest and this crest goes down. Now, because the wavelength, so I want you to take your hands for a minute, okay, pretend you have like some Play-Doh or whatever in between your hands. If you squish it together, all right, that Play-Doh has to go somewhere. That's what makes the wave higher. Okay, that's what makes your wave height higher. All right, as waves get closer to shore, they get bigger. Boom. Cool. All right. So we know in an earthquake, or excuse me, in a tsunami, the earthquake is what's providing the energy. Obviously, all waves are not tsunamis. That would be horrible. That would be super scary. Nobody would ever want to go to the beach. All right. So if it's not an earthquake making the energy, how does the energy get there? Where does the energy come from? Okay. How come this wave is being produced? This is not a tsunami. This is just your regular run-of-the-mill wave. It comes from wind, which is an important part of what we're going to talk about tomorrow. All right, wind energy All right. Wind moving across the surface creates this shear force. All right. And that is what is causing this movement of energy to begin in the seawater. All right. When you're talking about waves that are originating from wind, you have something called the fetch. The fetch is the distance that the wind can move over water. All right, so if we imagine like a really windy day at the beach, all right, the fetch is going to be a lot longer. All right, the wind is going to be able to travel a greater distance, and that means you are going to have a larger and stronger wave because you have a greater distance that this energy is traveling. We're adding more energy to the water. Whee. All right. So that's how waves start. Good old wind. Also tides, which let's talk about that for a second. We've talked about this, but it's a fine and dandy day to review. It's always a good day to review. We remember that tides are caused by the moon's gravitational pull. All right, remember it's the moon's job, or it's the moon that's doing the majority of the work because the moon is closer, even though the moon is smaller. It's smaller. It has a bigger influence than the sun because of its proximity. All right. We remember with tides, we have our two different types of tides. We have our spring tides and our neap tides. A spring tide happens during a full and a new moon when the earth, moon, and sun are in a straight line. So remember, straight is spring. And when that happens, you have really high tides and really low tides. So a greater difference between high and low. That's what we mean by enhanced here. During a quarter moon, when the moon looks like it's cut in half, that's our 90-degree angle. The moon, sun, and earth are at a 90-degree angle. The tides are smaller in difference. So you'll have lower high tides, but higher low tides. And that's called a neap tide. All right. For my friends that maybe weren't here during the astronomy unit, here's the diagram for that. If you were here, it's a nice little review. So up top, we have our spring tides because it's in a straight line. All right. Here's our new moon where we can't see the side that's facing us, or the full moon, the side that's facing us is fully illuminated. Here, the sun and the moon are basically on the same tug of war team. All right. They are both pulling water to the high tide side, which means there's less at the low tide side, which are these right here. Okay. During the neap tide, all right, the moon's still the one that's in charge. The moon is still causing the high tide. So the moon is pulling the water to the high tide side, which in this case is here where the light blue is. But the sun's like, no, I'm going to pull some of this water back to the low tide side. And that's why there's less of a difference. Look at us for view and astronomy in the hydrosphere unit. Good job. All right. So tomorrow we will cover ocean currents. We'll dive into that. Pun fully intended there. Pun fully intended. All right. What you're going to do now, you're going to review these terms that you should have picked up through the notes and take a look on Canvas for your next instructions.